All right, we're back. We've been talking about oscillations, and we have found a couple of general forms for a solution to the equation of motion x double dot is minus omega squared times x. One solution that we found was given by a sum of trig functions uh, like this. Let us recast that in a slightly different way. We can imagine a triangle with constants b1 and b2, and there's some angle delta here and some hypotenuse a, and let's let a equal, according to this triangle and Pythagoras, the quadrature sum of those two terms is the square root of the quadrature sum of those two terms is equal to a. Also from this figure we see that sine of delta is equal, so that's opposite sine, so opposite over hypotenuse, so that is sine of delta is b2 over a, and likewise the cosine of that angle is the adjacent over the hypotenuse, and that's adjacent is b1 because delta is here and b1 is the adjacent, so that's b1 over a. Okay, so that means that we can take this thing and we can do a fancy trick. We can multiply and divide both terms by a. It's not all that fancy of a trick. Cosine omega t plus b2 over a sine of omega t, and we'd multiply the whole thing by a. So these two, this function here and the one I just wrote are the same. But b1 over a is cosine of delta, and b2 over a is the sine of delta. So that means that this is a times cosine of delta times cosine of omega t. And delta is just a constant, and you're going to see in a second that a and delta are excellent constants to set the initial conditions, just like b1 and b2 were up there. That's where we're going here. And let's finish though. b2 over a is sine of delta, according to these equations. Sine of delta times sine of omega t. All right. And now it's particularly obvious what a is. These sines and cosines, are always trapped between plus and minus 1. That's no matter what you're taking the sine or the cosine of, the largest that function, that result can be is plus minus 1. So that makes it particularly explicit that this thing here, a, is the amplitude of the motion. That is the largest x one could get. And the next thing we recognize is that this thing, that, we can, there's trigonometric, why does that sound so weird? Identities, the cosine of an angle, of the difference between two angles, A and B, is cosine of A, cosine of B, plus sine of A and sine of B. That's just a trig identity that you need to know. Here we have A is equal to omega t and B is equal to delta, right? Because we're looking at this form. That then if you do this replacement, you find that this equation, x of t, then becomes a times cosine of omega t minus delta. All right, so now this is yet another solution for our harmonic oscillator, and it has, and this gives us the position as a function of any time. It only has one term in it, though. Before we had two terms. Up here we had two terms with two constants, but here we only have one term, but we still have two constants, a and delta. Those are still needed to describe the initial position. Those are the initial conditions, a and delta. And a we identify as the amplitude, and delta is the phase. When t equals 0, at t equals 0, we have that x of t, t equals 0, is equal to a times cosine of minus delta. And this is some number that is some fraction of 1, possibly with a sign. So in this case, the oscillations are lagging behind a simple cosine solution by this phase shift delta. So you can imagine we could start the object here, or we could start the object here, or we could start the object here. And this lag here is basically this delta quantity, and I drew this in such a way that all the amplitudes were the same, and what was changing was delta. So this is yet another form of the full solution. This is a completely general solution to our equation of motion. And these constants a and delta we'd need to figure out from the initial conditions. All right. Yet another solution. Hello. Yet another solution is the real part of a complex exponential. I'm going to look at what's coming up. I think I'm going to leave so there's the real part of a complex exponential also leads to another general solution, and it's actually kind of neat, but I'm going to make that a separate discussion. I may do it in class. Probably be better to do that in class. Because it's a little touchy, it's something I want to practice with together. So I'm gonna postpone that discussion, and I'm gonna turn now to energy considerations. When it comes to harmonic oscillators. All right. So let us recognize that x of t, a perfectly good solution to our. Here's the equation of motion. The answer is x as a function of x of t, and this guy is the two derivatives of that. And this equation of motion asserts that the original function and its second derivative are related by a negative constant. That is SHO, baby. All right, and from that we found a number of different ways. Number of different forms of the solution that one could use. But let's look at this guy. There is the position as a function of time, so the potential energy, which is 1/2 kx squared, thus equals 1/2 k times a squared cosine squared omega t minus delta. We just put x in there. So this literally is, you could use this to plot the potential energy U of x versus time. U of x versus time. Because you know the position as a function of time, and the potential energy is a constant times that position squared. Okay, so that is the potential energy as a function of time. Apparently, somebody was speeding in Niterói. Sorry about that background noise. So with this functional form for the position, we can write the velocity as a function of time. This is, again, as I said, the velocity, not the speed. It is a vector. It has a sign. The sign is the direction. In a one-dimensional coordinate system, the sign is the direction. If the sign of a vector is positive, that means that vector is pointing in the same direction as the positive direction of your coordinate system in that one dimension. All right, so we could take the derivative of this function, and we get minus a omega sine of omega t minus delta. So this is the velocity. At any time, you could calculate the velocity using this equation. The kinetic energy, T, is 1/2 times m times the velocity squared. And if we write it in the way that is suggestive, we can then put this guy in there. And then that means that the kinetic energy at any time is 1/2 times m times this thing squared. So that's a omega squared minus a omega, if you want, sine squared omega t minus delta. Which is equal to 1/2 m a squared omega squared sine squared omega t minus delta. That's T. This is T, the kinetic energy of your oscillator as a function of time. You can plot it, or you can evaluate it. You could also have evaluated as a function of time the potential energy. So here's the kinetic energy. This is the Ke, and this is the Pe. Okay, and we see from these forms. Well, hold on. Let me do one thing first. We have defined omega squared as k over m, right? So that means that m omega squared is equal to k. And I have m omega squared there and there. So that means I can write the kinetic energy as 1/2 m omega squared is k times a squared times sine squared omega t minus delta. All right, so here we go. So this is the kinetic energy. K is the spring constant again, which again is defined for the problem. It's a constant for the problem. All right, and here up here at the top was the form of the potential energy. So you can see, just looking at this equation, you know that no matter what's going on, cosine squared of something is between plus and minus 1. Well, it's actually between 0 and 1. And likewise, sine squared of anything is also between 0 and 1. So then we see from these two equations, the potential energy and the kinetic energy oscillate, just because here's the explicit forms. They oscillate between 0 and 1/2 Ka squared. And when you when the potential energy is as large as it can be, which means that this omega t minus delta is equal to 0, which makes the I'm looking here. If u of x is let's write this out. So u of x, or u, just u is equal to 1/2 k a squared where did I put it? Cosine squared omega t minus delta. All right, so this thing will always be greater than or equal to 0 and less than or equal to 1. And the kinetic energy we got was 1/2 k a squared sine squared omega t minus delta, and likewise this thing will stay between plus minus 1, 0 and 1. But because these are sines and cosines, when u is maximal, that means that t equals 0. And likewise, when t is maximal, then u is equal to 0. So the total energy, E is t plus u, then equals 1/2 k a squared, which was t. T is sine squared omega t minus delta, plus 1/2 k a squared cosine squared omega t minus delta, which is equal to 1/2 k a squared times sine squared plus cosine squared. I'm not going to write the omega t minus delta in both times. This was t and this was u, and we brought the k a squared out, and this quantity, no matter what's inside there, is equal to 1. So that means the total energy of a harmonic oscillator is 1/2 k a squared. And let's note, this is a constant versus time. There's no time in this equation. There's no cosine or sine of some function of time. This is just a number. Once you've set up your harmonic oscillator, you've built the thing. You've got some spring. You chose how stiff that spring was, and you chose how heavy the mass that you attached to it was. You picked those two things, and you built it. So now omega is k over m, and that's a constant. And you're gonna displace this thing from its equilibrium point by some amount. That is the amplitude. So whatever amplitude the motion has, the quantity 1/2 times k times a squared will be the total energy. And this is a constant, and it must be a constant because F equals minus kx is a conservative force. It is curl-free. It depends on position only. So it is a conservative force, and you can derive the potential energy from it. And so conservative force, energy is conserved. And that means that the energy is given by 1/2 k a squared forever. The energy will never change. Once you've built this thing and thus given it some value of omega, and you've displaced it by some amount, that displacement has injected energy into the system, and that energy, you will never, ever lose it. Okay? All right. So let's turn now to another kind of oscillator, and that's a two-dimensional one. We started out with a force F is well, in one dimension we had F is equal to minus kx. That was our one-dimensional. It could be a spring and a mass, or a pendulum also fits into this if the oscillations are small. We can also, though, imagine a harmonic oscillator in two dimensions that is, quote, isotropic, which is to say minus kr. So if you had say a two-dimensional space x and y, then if you displace the object in this direction, say you pulled it off this way, imagine a pendulum hanging from the ceiling, but it's not constrained to one dimension. It can oscillate back and forth and towards you and away from you. And so now I'm looking in this view here, I'm looking at above. I'm looking from above. So here's a pendulum, and I can pull it away from its equilibrium point. And if I look at it from above, this thing, though, I can pull it away from the equilibrium point in any direction. I could pull it away this way, or I could pull it this way, or I could pull it that way. All right. Well, what happens if I do that? Let us pull it away in this direction. All right. I'm looking again. This view is from above. All right. Now, if the force looks like this, and with this minus sign, that means that the force is going to be pointing back towards the origin. If I've displaced it in this direction, the force is going to be back towards the origin. And if I displaced it in this direction, the force is going to be back towards the origin. This is a vector equation, and the minus sign ensures that if I displace off in some direction, the force will be pointed back towards the origin. All right, so and of course the equilibrium point is at the origin. I drew this as a pendulum. You could also imagine a bowl, a two-dimensional bowl, and you could put a marble in the bowl. But whatever place you put the marble in, it's going to go back towards the middle. It's going to want to go towards the middle, the bottom lowest point of the bowl. That's another example of a 2D oscillator. Is a grape in your salad bowl, or a Fruit Loop in your cereal bowl. Okay. This equation F is equal to minus K R these are Cartesian coordinates equivalent to two equations of motion, all right. And effectively, in our spring, if you want to think about it, you can imagine that you have a mass which is attached to four springs like this, each with a spring constant K. And since all of these K's are the same, then the omegas, these omegas here, have to be the same. And omega is related to these K's and the mass of the little thing that I put here with this equation. So these are, if you have springs, four springs in a two-dimensional space, and I displace the object this way, it's going to start oscillating back and forth like this. And if I displace it with that amplitude, it's going to oscillate back and forth in that amplitude. And if I displaced it this way, it'll oscillate back and forth this way with some amplitude. All right, we already know that what the solutions of this are. We have x of t is equal to some amplitude in x times cosine omega t minus delta of x. Where I start this this phase, that's an initial condition in x, and there's an amplitude in x, and in the y direction we have an amplitude in y times cosine omega t minus delta y. So here in this case there's four constants that we need to figure out with the initial conditions. There's the amplitude of the x motion. You could imagine if the object was going back and forth like this, then the amplitude in the x motion is only that much, but the amplitude in the y motion is that much, x and y, right? So you can see that you can have two different amplitudes in the two different directions, and of course you can have two different phases. We can, though, fortunately set the time origin to get rid of one of these phase angles, such that x of t is a to the x cosine omega t. We've set the time origin such that it eliminates this little dx. And I'll show you how in a second. Y of t is equal to ay cosine of omega t minus delta. But here this delta is delta x minus delta y, and that's how we got rid of it. It's the relative phase of the x and y oscillations. So that means now we have three constants, ax, ay, and delta. Okay. So if ax happens to be 0, then obviously these two equations give, if ax is equal to 0, then what we have is simple harmonic oscillation in the y direction. If ay is equal to 0, then we have simple harmonic oscillation in the x direction. The x of t and y of t are the x and y positions of the mass. That is the answer. And if so, in the first case, if ax is equal to 0 in my spring example, if ax is equal to 0, then that's harmonic oscillation in the y direction only. And if ay was equal to 0, then it's harmonic oscillation in the x direction. But if ax and ay are not equal to 0, then obviously there's much more interesting things that are happening here. Let's draw a few pictures of that. So if ax and ay are not equal to 0, one type of motion we could have would be, so here's x. Again, if you want to think about this, you could think about, my pen keeps turning off, it makes me crazy. You could think about this either as a mass attached by springs in the x and y direction, or the top view of a pendulum that can move in 2 dimensions. If ax and y are not 0, but this delta quantity is 0, that means that the x and y motion are in phase, and the object is basically oscillating like this along this diagonal, and it moves between plus ax and minus ax and minus ay and plus ay. And this delta, let me write the full solution again so you have it in front of you, is x of t is ax cosine omega t, and y of t is equal to ay cosine omega t minus this phase. And if the phase in this example, the phase here is 0, so you could easily put a few numbers in here, and you'll see that as x increases, if x increases by this much, y is also increasing exactly that much. So it is oscillating along this diagonal back and forth. That's what this motion looks like when ax and ay is not 0, but delta is 0. That means that the x and y motion are completely in phase. They're synchronized, so to speak. The value of ax and the value of ay are the same. But delta doesn't have to be 0. There's other motions that exist and can be described perfectly well by these equations. And that is, for example, this one, y and x. And here's a motion. You can easily imagine a pendulum going around in a circle like this and oscillating between amplitude ay and minus ay and ax and minus ax. But when the value of y is maximum, the value of x is 0. And when the value of x is maximum, the value of y is 0. That's what happens here. And if you have some motion where you have even smaller delta in that range, let's say delta is pi over 4. Then the motion looks like this, x and y, and that's not very well centered, but I can do that in post-processing, something like that. And now we get, there's ax, there's minus ax. Those are the extreme positions it can get to in x, and here's ay, the amplitude in y, and there's minus amplitude in y. So this is another motion, a perfectly valid motion that you could make if you took a pendulum and just gave it a little amount. If you displaced it and gave it a velocity in a certain direction, it would end up with this motion. And the value of this delta is controlling those different patterns, right? So depending on the initial conditions, you'll need to find ax, ay, and delta, and then once you have those three constants, then you can describe where the object is at any time. And then just to finish this up, we're going to now start with. We're going to take this one step further and make it an anisotropic harmonic oscillator, which is to say the spring constants on these different axes are different. So you can imagine in 2 dimensions we have a mass, but it's attached by very big springs in the x direction, massive, heavy springs. But in the y direction, it's only attached by wimpy little ballpoint pen springs. So that means that there's going to be a spring constant kx and a spring constant ky, which are different. And so our equation of motion is f of x, well, our force is minus kx times x, and our forces are minus ky times y. If this would be three-dimensional, f of z would be minus kz times z. But these forces then lead to the equations of motion of x double dot is minus omega squared of x times x, and y double dot is minus omega squared y times y, with x of t and y of t being the answer. And then we do the same trick we did before. We define the time origin such that either the x or y phase is 0. And then the motion depends just on the relative phase of delta equals dy minus dx, x. And then we get the solutions x of t is equal to ax cosine omega x of t, and y of t is ay cosine omega y of t minus delta, with omega x being the square root of kx over m and omega y being the square root of ky over m. So these different spring constants in the two different directions, the spring constant in the x direction will be it's a much heavier spring, stiffer spring, pulling the force a certain distance, pulling the mass a certain distance will require a lot of force. So kx is in one of the spring constants, it's much larger than ky. But in the x motion, you need to use the omega for the x spring constants, and the y motion for the we'll use the spring constant for the y springs. Okay. In this situation, obviously, there's a much richer set of solutions, and I think also I want to pick this up when we get back into class so we can draw pictures together. But the bottom line is if these two omegas, if the ratio of these omegas is a rational number, which means it's not a fraction with an infinite number of terms of numbers. Like if omega x divided by omega y, it depends on this quantity, and if that is a rational number, like 6. An irrational number like pi has an infinite number of digits. If it's a rational number, then the motion will repeat, and you end up with things called Lisa. I don't even know how to pronounce that. Figures, and you can imagine, they are the motions of pendula. They can have all sorts of different interesting forms. But even in that situation, the motion will eventually repeat if omega x and omega y is rational. And if omega x and the ratio omega x to omega y is not rational, then the motion will never repeat. And this is quasi-periodic motion. The mass will never come back to the same place, moving in the same direction as it did before. The motion will never repeat. The motion in the x coordinate is periodic separately, and because they're each given by these equations. The x motion will be periodic, and the y motion will be periodic. But if omega x divided by omega y is irrational, the motion of r, the motion of the actual location of mass, will never repeat. And I'll talk about that in class. The other thing we're going to talk about in class is damped oscillations. We're going to put together the drag information, the drag tools, the skills that you learned with drag early on in the class, and we're now going to put that together with our harmonic oscillator, and we're going to come up with something called damped oscillations. And you're going to see it's pretty straightforward. Okay, so this is all I wanted you to think about for now. And please read Chapter 5 of Taylor. And I look forward to seeing you on Monday. Take care, everybody. Thanks a lot.